When sizing conductors for transformers, the primary consideration is the allowable overcurrent protection device as outlined in Section 430.3b of the National Electrical Code, not the transformer's inherent ampacity. Section 430.3b specifically addresses the ampacity requirements for conductors running from transformers to overcurrent protective devices. This section mandates that the ampacity of these conductors must not be less than the values provided in Table 430.3b. The values in that table correspond to the maximum allowable percentage of the transformer's nameplate current, as determined by Section 430.32. To properly size the conductors, firstly, determine the transformer's primary and secondary nameplate currents. These values are crucial as they form the basis for subsequent calculations. Secondly, consult Section 430.32 of the National Electrical Code to ascertain the maximum allowable overcurrent protection for the transformer. This section provides guidance on the appropriate percentage or specific ampere rating for the overcurrent device. Thirdly, refer to Table 430.3b of the National Electrical Code. This table correlates the maximum allowable overcurrent protection percentage with the minimum required conductor ampacity. The table will guide you on the minimum ampacity that the conductors must possess based on the permitted overcurrent protection level. Fourthly, select conductors that have an ampacity equal to or greater than the value obtained from Table 430.3b. It is imperative to choose conductors whose ampacity meets or exceeds the calculated minimum to ensure safe and compliant operation. Fifthly, consider any applicable correction or dirty factors. Factors such as ambient temperature, the number of conductors in a raceway, and other environmental conditions can affect the conductor's ampacity. Apply appropriate correction and dirtying factors as necessary to ensure the selected conductors can safely carry the required current under actual operating conditions. Let's delve deeper into the practical application of these principles. Imagine a transformer with a primary voltage of 480 volts and a primary current of 25 amps, and suppose Section 430.32 permits an overcurrent protection device rated at 250% of the transformer's primary current. This would mean that the maximum allowable overcurrent protection device would be 250% of 25 amps, which equals 62.5 amps. In this scenario, you would consult Table 430.3b to determine the minimum required conductor ampacity corresponding to this overcurrent protection level. Table 430.3b would guide you on the appropriate conductor size needed to handle this level of overcurrent protection safely. Now, let's consider another scenario where the transformer's primary voltage is 208 volts and its primary current is 50 amps. In this case, let's assume that Section 430.32 allows an overcurrent protection device rated at 125% of the transformer's primary current. This means that the maximum allowable overcurrent protection device would be 125% of 50 amps, which equals 62.5 amps. Again, you would consult Table 430.3b to determine the minimum required conductor ampacity corresponding to this specific overcurrent protection level. This ensures that the conductors are adequately sized to handle the potential overcurrent conditions. In another example, consider a transformer with a primary voltage of 277 volts and a primary current of 10 amps. If Section 430.32 permits an overcurrent protection device rated at 150% of the transformer's primary current, the maximum allowable overcurrent protection device would be 150% of 10 amps, which equals 15 amps. In this instance, you would refer to Table 430.3b to determine the minimum required conductor ampacity corresponding to this particular overcurrent protection level. This will guide you in selecting the appropriate conductor size to ensure safe and compliant operation under these conditions. It is important to note that the specific values in Table 430.3b may vary depending on the edition of the National Electrical Code being used. Always consult the latest edition of the code for the most accurate and up-to-date information. Moreover, it is crucial to consider the specific characteristics of the transformer and the installation environment when selecting conductors. Factors such as the type of insulation, the ambient temperature, and the presence of other conductors in the same raceway can all affect the conductor's ampacity. Ensure that you apply appropriate correction and directing factors as necessary to account for these variables. Furthermore, always adhere to all applicable local and national electrical codes and regulations when sizing conductors for transformers. These codes and regulations are designed to ensure the safety of electrical installations and to prevent electrical hazards. Failure to comply with these codes and regulations can result in serious consequences, including electrical fires, equipment damage, and personal injury. In addition to the above considerations, it is also important to consider the voltage drop in the conductors. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause equipment to malfunction or fail to operate properly. To minimize voltage drop, it is important to select conductors that are large enough to carry the required current without excessive voltage loss. The National Electrical Code provides guidance on acceptable voltage drop levels for various types of circuits. When sizing conductors for transformers, it is essential to consider both the ampacity requirements and the voltage drop requirements to ensure safe and reliable operation. In summary, the process of sizing conductors for transformers involves several key steps. Firstly, determine the transformer's primary and secondary nameplate currents. Secondly, consult section 430.32 of the National Electrical Code to determine the maximum allowable overcurrent protection for the transformer. Thirdly, refer to table 430.3b of the National Electrical Code to determine the minimum required conductor ampacity corresponding to the allowable overcurrent protection. Fourthly, select conductors that have an ampacity equal to or greater than the value obtained from table 430.3b, considering any applicable correction or directing factors. Fifthly, consider the voltage drop in the conductors and select conductors that are large enough to minimize voltage drop to acceptable levels. By following these steps and adhering to all applicable codes and regulations, you can ensure that the conductors are properly sized for the transformer, providing safe and reliable operation. Remember that electrical work can be dangerous, and it is always best to consult with a qualified electrician if you are unsure about any aspect of the installation. It is also crucial to understand that the National Electrical Code is a complex and comprehensive document, and it is essential to have a thorough understanding of its provisions before undertaking any electrical work. In addition to the above, it is also crucial to consider the specific application of the transformer. For example, if the transformer is supplying a critical load, such as emergency lighting or life safety equipment, it is essential to ensure that the conductors are sized to provide the highest level of reliability. This may involve selecting conductors that are larger than the minimum required by the National Electrical Code. Furthermore, it is also important to consider the potential for future expansion or changes in the load. If there is a possibility that the load may increase in the future, it is prudent to select conductors that are large enough to accommodate the anticipated increase in load. This can help to avoid the need for costly and disruptive upgrades in the future. When selecting conductors for transformers, it is also important to consider the type of conductor material. Copper conductors are generally preferred for their high conductivity and corrosion resistance. However, aluminum conductors may be used in some applications provided that they are properly sized and installed. Aluminum conductors have a lower conductivity than copper conductors, so they must be larger to carry the same amount of current. In addition, aluminum conductors are more susceptible to corrosion than copper conductors, so they must be properly protected from moisture and other corrosive elements. Another important consideration when selecting conductors for transformers is the type of insulation. The insulation must be suitable for the voltage and temperature of the application. There are many different types of insulation available, each with its own unique properties. It is important to select an insulation that is compatible with the environment in which the conductors will be installed. In addition to the above considerations, it is also important to ensure that the conductors are properly terminated. The terminations must be clean, tight, and properly insulated. Poor terminations can cause overheating, voltage drop, and even electrical fires. It is also important to ensure that the conductors are properly supported. The supports must be strong enough to hold the weight of the conductors and to prevent them from sagging or touching other objects. Sagging conductors can be a safety hazard, and they can also reduce the efficiency of the electrical system. Finally, it is essential to thoroughly inspect the completed installation to ensure that it is safe and compliant with all applicable codes and regulations. The inspection should include a visual inspection of the conductors, terminations, and supports, as well as electrical tests to verify the integrity of the installation and the continuity of the conductors. By following these guidelines, you can ensure that the conductors for your transformer are properly sized and installed, providing safe, reliable, and efficient operation. The selection of appropriate conductors is a critical aspect of transformer installation and directly impacts the overall performance and safety of the electrical system. Therefore, careful consideration should be given to all relevant factors to ensure optimal results.